Hi, guys. All right, welcome back to our continuing discussion of protein stability. So, we've been talking about the thermodynamics of protein stability. We've looked at an example protein, RNase A, and we've seen how that protein, as we'd expect, has a negative free energy for the transition from the unfolded to the native state. And we broke that down. We looked at the enthalpic and the entropic components. We saw there's a strong enthalpic driving force to form the folded state, but a big entropic barrier to folding, right? And so we've got these compensatory forces, large going in the opposite direction, and the small residual is that stabilizing free energy of about 45 kilojoules per mole for RNase A. So where is the driving force coming from that stabilizes a protein ultimately? And I pointed out last time comes from basically two areas. Comes from both the hydrophobic effect and those weak interactions. So let's, in this section, let's talk a little bit about how the hydrophobic effect impacts protein stability. Now, recall from our discussion of protein structure, especially globular protein structure, where are all the hydrophobic amino acids in a well-folded globular protein? They're on the inside, right? They're all clustered up together, packed and shielded from solvent, right? Now, in an unfolded protein, however, that's not true. The hydrophobics get exposed to solvent, right? So that has implications, right? So if you imagine an example of an unfolded protein here, and here have like a nice little phenylalanine in our unfolded protein to represent the hydrophobic amino acids. If that's exposed in water, we know what's going to happen is that's going to result in this formation of these little water clathrates, these partially ordered water around those hydrophobic amino acids, right? And we know there's an entropic penalty associated with that. We discussed that when I introduced you guys to the hydrophobic effect. So if this protein then folds under a free energy balance less than 0, we know what's going to happen when the protein then folds up. If we take that phenylalanine and we bury that down in the core of the protein, when that molecule folds up, what happens to all those ordered waters, right? They're not going to be down in the core. They're going to get released, right? So we're out here, we're free, yay, doing our things, tumbling about in solution, going about our business, hydrogen bonding like bulk water, right? So that burial of those hydrophobic residues leads then to the release of ordered water as a direct consequence of the burial clustering of those hydrophobic amino acids in the core of the protein and the release of these ordered water molecules, which means then that for this process, right, the change in enthalpy, right, for the water upon going from the unfolded to the native state, right, is going to be much greater than 0. And remember our discussions about the second law. That's a favorable thing, right? The increases in entropy are sort of favored by the general energetic design of our universe, right? So that's an extremely favorable thing. And that's obvious also if you look again at the Gibbs equation. But if you also remember our discussion from the last time about the change in the configurational entropy of the polypeptide itself going from the unfolded to the native state, we saw that that is going in the opposite direction, right? We've got to take all those conformational states available to this unfolded polypeptide, right? This thing is all over the place and possible different configurations, right? We know that. Collapse those guys down to one state, that's a big loss in entropy. So one of the ways to think about this is that release of ordered water, that increase in the entropy of the water upon folding compensates for the loss of entropy in the polypeptide chain. So the magnitude of this penalty gets reduced by the increase in entropy of ordered water. Right. All right. So that's a That's a cool thing, right? So that's a major contribution to the folding of a protein, the stability of a protein, is that release of ordered water, right? All right, but at this point, we have two problems. One, um, has to do with the magnitude or the primacy um, of the hydrophobic effect in folding, or I should say in stability, protein stability. Right? People for a long time thought and taught that this effect, the hydrophobic effect, was the main thing. Everything else was sort of like second or third order for holding, maintaining the stability or keeping a protein stable, right? And what we're going to see is that while it's super important, it's not the only thing, right? There's significantly more to it than that. Okay, the second issue comes up here, has to do with the way in this is frequently presented, which is basically it's fairly common for people in discussing the hydrophobic effect, especially in the context of protein folding, to equate the hydrophobic effect with this increase in the water entropy, right? And the problem is that that's wrong, okay? So the hydrophobic effect is not equivalent to the simple increase in the water entropy. The increase in water entropy, or the entropic penalty of putting hydrophobic stuff in water, is a component of the hydrophobic effect. But the simple-minded way this is often presented, that those are exactly the same thing, is incorrect. And if you think about it that way, there's some important things in protein folding you really can't understand correctly. All right, so let's see if I can set this on a correct footing for you guys. So let's think again about the definition of the hydrophobic effect. What really is it, right? I talked about it the last time. What does the hydrophobic effect really mean, right? It's really as simple as possible. If you think back to that transfer experiment that we talked about a couple of lectures ago, the hydrophobic effect is simply the tendency of hydrophobic stuff in aqueous solutions to clump together, right? It's really that is the definition of the hydrophobic effect. The question now we're grappling with is what makes that happen? And we talked about that a little bit the last time, and I pointed out there are several different things, right? If you take an aqueous solution like this, right, and you put hydrophobic stuff in there, the water's got to make a cavity, right? It's got to do something. It's got to rearrange because you're shoving mass in there. It's got to make a cavity. And that does several different things, right? It disrupts the H bonding network of the bulk water, right? Because you've got cavity of stuff in there and the waters can't get to each other. And so that disrupts the normal hydrogen bonding network in bulk water. That's enthalpically expensive. The other thing is that water can't form good van der Waals interactions with non-hydrophobic stuff. I mean, think about those dipoles and those paired valence electrons on the oxygen and the dipole or the molecular dipole. There's nothing for it to interact with hydrophobic stuff. It can't align with anything. The London dispersion forces are not nearly as good between water and the hydrophobic stuff as it is between the hydrophobic stuff and itself, right? So there are, little good van der Waals between the water and the hydrophobic. And at the same time, there are very good van der Waals between the hydrophobic and the other hydrophobics, right? They're excellent van der Waal interactions when those guys clump up with each other. And at the same time, right, when we make this cavity, right, the water is part of the process of minimizing the energy penalty, right? That's it caused by forming this cavity, disrupting these hydrogen bonds. We don't get a lot of good van der Waals interactions. The water molecules, to in part compensate, form these clathrate-like structures around the outside, the surface of the hydrophobic stuff, because they can't ionically interact, they can't electrostatically interact, they can't van der Waals interact, but they can interact with each other. And these high residence time water molecules on the periphery, these clathrates, compensate for some of that loss of energy that the water would normally have had with itself, but I shoved a chunk of stuff in there that can interact, right? They're entropically expensive, but enthalpically, there's some decent gain there, right? Those long residence time hydrogen bonds are stabilizing, right? So all of that, right? The energy balance for all of that at, say, 25 degrees leads, along with the tendency of the hydrophobics to interact with themselves better, and, you know, minimizing waters in those clathrates leads to this sort of surface area minimization that we talked about the last time. The tendency of the hydrophobic stuff to cluster up in a larger volume and minimize the amount of water molecules tied down in these clathrates. Okay, now the problem with thinking of, as people often present it, equating the hydrophobic effect with simply that tendency of or the entropic penalty of putting hydrophobic stuff in water. Where that becomes a serious problem is when you think about the temperature dependence. Of the hydrophobic effect. Okay. Now it helps in sort of going through this argument if, rather than thinking about the hydrophobic effect as sort of this complicated thermodynamic problem, or thinking about water collapse, whatever, one of the things that helps here is if you think about the hydrophobic effect in a somewhat different conceptual way, you think about it as being related to solubility. In other words, the hydrophobic effect, to some extent, really is an expression of how soluble hydrophobic stuff is in water, which is not very, right? So what we're going to be thinking about here, essentially, is the solubility, how the solubility of hydrophobic stuff in aqueous solution varies with temperature, right? Okay, so what you may not know, or if you think about it, well, you may not, like I said, well, if you don't know anything, you don't know it, you think about it, it doesn't do any good. But what you may not realize is the answer to the following question, which is, what happens to hydrophobic interactions as the temperature increases? Do you guys know this? Anybody know? Pause for a minute. Maybe you've heard this before. Turns out, as the temperature increases, hydrophobic interactions get stronger. So as the temperature goes up, the hydrophobic effect gets stronger. Or another way to put this is as the temperature goes up, the solubility of hydrophobic stuff goes down, right? And that may not be something you guys are familiar with, but it's true. It's experimentally demonstrable. And this has a really interesting consequence when you then think about one of these partitioning equilibria between an organic solvent and water, and you look at the thermodynamic distribution of what's going on, right? So we're going to think about that sort of equilibrium, again, partitioning equilibrium again, but I'm going to reverse it because it's the way it's often shown. So here's my hydrophobic molecule, sort of like insolvent or interacting with itself or whatever. And we're going to think about a transfer equilibrium here. We're going to transfer one of these hydrophobic molecules into water, right? And we're going to have something like this, right, in water. And we know we can have an associated, we can measure that equilibrium constant like we did last time. We know we're going to have an associated transfer free energy. I'll just give it C delta G TR, right? And we can measure that, and then we can break it down, right, into the component entropy and enthalpy contributions like we saw before. So if you do that, right, and you plot this out, you see something that's actually pretty amazing, which is this distribution looks something like this. All right, so temperature on the y-axis, or excuse me, on the x-axis, and we'll be at like 0 degrees here, 50 degrees, and we'll just call this degrees Celsius. 100 degrees, 150 degrees, right? And on this axis, we're going to have free energy. So in kilojoules per mole, right? So we're looking at the free energy change. We're looking at the impact of temperature on that transfer free energy. And it's unfavorable, right? So up here, this is 0. And so up here we'll have, you know, I don't know, plus 10, plus 20, plus 30 kilojoules per mole. And down here we'll have minus 10, minus 20, minus 30 kilojoules per mole, right? So above this line, transfer is unfavorable. Below the line, the transfer would be favorable. Well, we know, and at all these temperatures, this isn't very favorable. The transfer free energy basically looks something like this. It's never favorable, right? So the delta G for transfer is always positive, right? There's never a situation across this temperature range where you can make that transfer from the organic into the aqueous favorable. But check this out. When you break down that transfer free energy into its constituent parts, what you find is that the T delta S component does something like this over here at so this is T delta S, right? And then if we look at the enthalpy change, it does something like this. Right? So if this is delta H, right, and that line is not quite right. Right? I think my scale is off a little bit here. Okay, that's close. Okay, so here's the point. If you look at it and you think about that really hard, think about this point right here. Think about what that means, right? Right there. What's that telling you? We're looking at the entropy of transfer from organic into water at this temperature, 150 degrees, right? I know it's a little weird, 150 degrees, but it still makes a really important point. At that temperature, right, the transfer, the entropy penalty, the transfer entropy is 0. Or another way to put it is the transfer entropy penalty is 0. Now think about that. What that means is there is 0 entropic penalty for transferring one of these organic molecules out of a solvent into water at 25 degrees. There's no entropic penalty, which means the water clathrates don't even form. They're not stable. They can't form. There's no entropy cost to making this transfer. And yet, despite that, if you look at the transfer free energy, it is still extremely large and extremely unfavorable, right? Which means the reason that the transfer is unfavorable at this point is because it's dominated by an unfavorable enthalpy change. Okay, so the way to think about this, all right, is that at this temperature, even though the entropy cost of that transfer is basically 0, the clathrates can't form, yet the hydrophobics are still insoluble, which means the hydrophobic effect is still very, very strong, right? Really strong, and yet you can't form a water clathrate. So the hydrophobic effect can't be equivalent to the entropic penalty, right? At this point, right, it's the unfavorability of the loss of enthalpy, right? The fact that you can't form the bulk water interactions, the fact that the temperature is now disrupting the ability of these hydrophobic guys to interact with themselves in a solvent where they can't interact, that becomes so incredibly unfavorable that the enthalpy now dominates the free energy. This also has interesting implications down here, right? If you think about what's happening down here, at this point, right, if you look at this, you look at what's happening to the enthalpy change, it actually goes from being unfavorable to being favorable. Well, the entropy is still, it's getting less and less and less. The entropic cost of forming the transfer or doing the transfer is getting less and less favorable. So what those two, and these are actual experimental measurements. I didn't just make this up. This is theory. People have actually done these sorts of experiments. Another way to think about this is that the water clathrate formation in temperatures down here, where we're talking about things, right? Especially with respect to protein folding. Clathrate formation, ordered water formation, while entropically expensive, is water's, I'm going to anthropomorphize here, is water's attempt to solubilize hydrophobic stuff. What this means is that as the temperature decreases, right, if the hydrophobic strength of the hydrophobic effect gets stronger and stronger and stronger as the temperature goes up, so the stuff gets less and less soluble. As the temperature goes down, the hydrophobic effect weakens. As the temperature goes down, the cost of forming those the cost of forming those water clathrates becomes less and less severe. The differential between bulk water and ordered water gets smaller, so the entropy cost shrinks. At the same time, you're now in a regime in terms of heat where you can form those hydrogen bonds, right? Those hydrogen bonds are worth of some significant stabilizing enthalpy, right? So as the entropic cost of forming those the entropic cost of forming that high residence time water goes down, right? As the temperature goes down, you gain from forming those those semi-stable hydrogen bonds, more stable than bulk water, you now tip the energy balance to the point that it becomes easier for water to form a larger number of those clathrates, or to have more of those water molecules tied up in surface areas, or in square angstroms of surface area, without as big an energy penalty. What that means is that the hydrophobic stuff, now there is a balance point, or a shift in dispersing that material out into solution with more water clathrate layers formed around these objects in more objects of more surface with a higher total surface area, becomes less and less energetically expensive, and the solubility increases as the temperature goes down, right? Okay, so that hopefully will help you think about a little bit about the hydrophobic effect in a slightly different way. It is a contribution of both this entropic effect here, right, as well as the enthalpic effect. And the primacy of one or the other, of which one is important, or at the point where they both become significant, is a very strong function of temperature. And the reason that matters is we now want to start thinking about the stability and folding of a protein as a function of temperature. And this effect then becomes significant for understanding how proteins behave at different temperatures.